In previous video, we have seen this radius ratio rule. So, according to that rule, like larger the cation, more number of anions can be packed around it in a particular size and shape. Okay, that is what our radius ratio rule was. And accordingly, thus knowing the size of anions, we should be able to predict the geometry. It's not the geometry, the crystal structure or type of packing we should be able to determine. So this is the table that you should by heart, or you should know this table. Then only you will be able to know which is the crystal type. Okay, so if the coordination number of cation is 8, then means a cubic 8. And if it's R plus by R minus range is greater than 0.732 or equal to 0.732, then it is a possible structure is that is a cubic. The crystal lattice will be cubic. Example is cesium chloride and cesium fluoride. Okay. And if the coordination number is 6, the possible structure is octahedral. If this R plus to R minus, what is this R plus to R minus? It is nothing but the rho, right? That is 0.4 to 0.7. And if it is 4, if coordination number is 4 and this range is between 0.2 to 0.4, then it is tetrahedral. Also, if it is from 0.1 to 0.2, it is triangular. So for tetrahedral, we have zinc blende and anti-fluoride structure. Okay, so see the example that for zinc blende, coordination number is or the R plus to R minus range should be from zero point 0.2 to zero point 0.4. Then only it will be behavior give a tetrahedral structure. But the point is, while calculating the using this radius ratio rule of R plus by R minus is found to be 0.5. 0.55 actually, it is in between 0.4 to 0.7. So, what is the range or the coordination number we should be according to this radius ratio rule? It should be an octahedral structure. But zinc blende and woodsite, they have a coordination number of 6. But predicted was coordination 6, but it is not correct. This is because of the covalent nature of zinc and sulfide. Okay. So, this is the point that radius ratio rules fails where the assumptions are not correctly followed. Many assumptions were there. Okay, the zinc sulfide failed because of the covalent character and polarization of zinc sulfide bond, which make this tetrahedral more stable than octahedral. Octahedral as predicted by the radius ratio rule. So we'll see the limitations of this radius ratio rule. This is the limitation. And because we assumed many things here, we assume that the size is not changing according to the environment. The size of ion is fixed. It's hard, rigid, it is fixed. That is our first assumption. Then we assume that it is only ionic bonding. No covalent bonding is found. We assumed only purely ionic bondings. That is according to Fagens's rule, small highly charged Zn 2 plus ion strongly polarized S2 minus ion. So, why this zinc blend Zn S bond is highly covalent is because of this Fagens's rule. Okay, Fagens's rule or something you can call it eitherly. So, according to Fagens's rule, small highly charged zinc, okay, zinc 2 plus ion strongly polarized with S2 minus ion, which makes the zinc sulfide bond a pure or more strong covalent character, which gives it more strong covalent character. So this covalent bonding, of course, it favors tetrahedral coordination rather than